Every week along the Grand Strand, oyster shells are getting a second life. Students at Horry Georgetown Technical College are partnering with the South Carolina Department of Natural Resources program to recycle shells and rebuild reefs across the coast.
Between 2007 and 2024, Florida dumped 500,000 tons of oyster shells into the Gulf of Mexico. Environmental groups called it ocean dumping. Fishermen feared it would destroy their grounds. Scientists set up monitoring equipment expecting to document a slow, expensive failure. What grew on those shells instead defied every prediction anyone had made, and the way it happened will change how you think about what the ocean actually needs. The experiment nobody believed. The program was not a grand scientific initiative with a large budget and extensive modeling behind it. It started from a much simpler observation. Florida's restaurants and seafood processing plants were generating enormous quantities of used oyster shells, and those shells were going to landfills. The Florida Fish and Wildlife Conservation Commission looked at the situation and applied a straightforward logic. The shells were going somewhere regardless. Landfills were one option. The Gulf floor was another. If the Gulf option failed, the result was waste relocated rather than waste avoided. If it worked, something potentially significant could happen. The shells were loaded onto barges and dropped at designated sites near Cedar Key on Florida's Gulf Coast. The backlash came quickly. Environmental organizations raised concerns about uncontrolled dumping in protected waters. Fishermen who worked the areas near the drop sites worried about what tons of shell material settling on the bottom would do to the sediment structure they had learned over decades of working those grounds. The concern about smothering was specific and reasonable. Introduce enough foreign material onto a productive bottom, and you can bury whatever was living there under something the existing ecosystem cannot adapt to. Charter captains who had built businesses on knowing exactly what lived where watched the barges unload and prepared for the worst. The FWC's position was honest about the uncertainty. Nobody had done this at this scale in this environment before. The models existed, but models are not ecosystems. The only way to know what would happen was to do it and watch carefully. They set up monitoring protocols, established baseline measurements, and waited. Nobody thought it would work this fast. The invisible phase. The first serious scientific check-in happened around 18 months after the initial shell deposits. Dr. Krimsky, one of the marine biologists assigned to monitor the Cedar Key sites, descended to the drop zones expecting to find shells under a layer of silt. Maybe some incidental colonization at the edges, probably a picture consistent with the critics' prediction that the shells would slowly disappear under the Gulf floor's natural sediment movement. What he found instead was explosive. The shells were not under silt, they were covered in life. The process that had started within days of the shells hitting the bottom begins with bacteria. A thin biofilm of bacterial colonies establishes itself on any available hard surface in the marine environment within hours, to days of that surface becoming available. This biofilm is not merely a surface coating, it is a living chemical signal. It changes the chemistry of the surface, releases compounds that attract the next wave of colonizers, and creates what marine biologists describe as living scaffolding for everything that follows. The chemistry of the shells themselves contributed something that bare sand cannot offer. Oyster shells are made primarily of calcium carbonate, specifically the form called aragonite. When aragonite dissolves slowly in seawater, it releases calcium ions that shift the local water chemistry toward alkalinity. This alkaline microenvironment is precisely what calcifying organisms, animals that build their own shells or skeletons from calcium, need to establish themselves. The shells were not just providing a physical surface, they were actively creating the chemical conditions that invite colonization. What followed, the bacterial layer built in predictable ecological stages. Diatoms and microalgae came next, feeding on the nutrients the biofilm concentrated. Then crustaceans and larval organisms of dozens of species arrived, drawn by the food the algae provided. Then juvenile fish, drawn by the crustaceans. Then larger fish, drawn by the juveniles. The food web assembled itself in layers, each layer creating the conditions that invited the next one, with the shell deposit as the foundation that made the entire sequence possible. The significance of this is most visible when you compare it to what happens on bare sand. Sand provides no purchase for the bacterial biofilm. It provides no calcium chemistry for calcifying organisms. It shifts with current and storm, preventing stable colonization by anything that needs a fixed surface to build on. The shells solved a problem that the Gulf floor in these areas had not been able to solve on its own, the missing ingredient that allows a food web to build from the bottom up rather than remaining a barren expanse. What came next made scientists rethink everything. The reef builders returned to understand what happened with the oysters. You need to understand a problem that had been quietly destroying Florida's oyster reefs for decades before anyone put shells in the water. Oyster larvae, called spat, are free-floating in the water column for a specific window of time after they hatch. During that window, they are looking for a hard surface to attach to. If they find one, they settle and begin developing into adult oysters. If they do not find one within the window, they die. The hard surface requirement is not negotiable and it is not flexible. Spat cannot settle on sand. They cannot settle on soft sediment. They need shell material, rock, or the shells of other oysters. Florida's natural oyster reefs had been harvested down to the point where large areas of reef habitat had been reduced to bare bottom. No substrate, no new generations. The reefs that had once provided the hard surface for new generations to attach to had been removed, and without them, each season's spawn was dying in the water column before it could find a landing site. The cycle was broken, and nothing in the ecosystem's natural functioning could repair it without the one ingredient that had been removed. The shells dropped by Florida's program were landing pads. Spat that had been dying for lack of substrate suddenly had millions of square feet of appropriate surface. The attachment rates Dr. Bill Pine documented at the Cedar Key sites moved well past what projections had suggested as optimistic outcomes. By the second year, the adult oysters that had established on the initial shell deposits were reproducing, adding their own shells to the reef structure, creating more surface for the next generation. By the third year, counts at the most productive sites were reaching 847 oysters per cubic meter on the shell reef, while comparable bare-bottom areas nearby registered near zero. Charter Captain Mike Lent had been among the fishermen most vocal about his concerns before the program began. He had worked those waters for years and was protective of grounds he understood well. He came back to those sites a few years into the program and spent time on the water near the reef sites, comparing what he was seeing to what he remembered. He came back to shore and said simply, "I was wrong." When the fish arrived, the results from the Cedar Key reef sites surprised even the marine biologists who were tracking them. Fish biomass increased by 340% compared to measurements taken before the shell deposits were placed on the seafloor. Species diversity increased by 280%. Numbers like these are extremely rare in ecological studies because ecosystems usually change slowly. When scientists see increases this large, it often means the environment has gone through a major transformation rather than a small improvement. From the beginning, researchers wanted to answer one important question. Were the reefs simply attracting fish that already lived nearby, or were they actually creating new fish populations? This difference is known as aggregation versus production. Aggregation happens when fish move from one place to another because a new structure offers shelter. It can make a location appear full of life without increasing the total number of fish in the region. Production is much more important. It means the habitat is supporting the birth, growth, and survival of new fish that would not have existed without the reef. The data from Cedar Key pointed clearly toward production. Scientists recorded unusually high numbers of juvenile fish living around the shell reefs. That suggested the reefs were acting as nursery habitats where young fish could grow safely through the most dangerous stage of their lives. On the open seafloor, small fish have very few places to hide from predators. The oyster shells changed that completely. Their rough surfaces and narrow spaces created thousands of tiny shelters where young fish could escape larger predators while feeding on the growing community of small animals attached to the shells. As the reef matured, the food web became more complex. Tiny algae covered the shells first. Small invertebrates followed, feeding on the algae. Larger crustaceans, worms, and mollusks then moved in, creating a rich food source for juvenile fish. Over time, larger predators arrived because there was now a reliable supply of prey. The reef was no longer just a pile of shells. It had become a complete living ecosystem. with every level of the food chain represented. The list of species continued to grow beyond what researchers had expected. Redfish, sheepshead, flounder, and snook appeared in much greater numbers, turning the reef into one of the area's best fishing locations. Octopus settled into the deep crevices between shell clusters. Sea turtles visited more often to feed on the dense populations of invertebrates living on the reef. Dolphins were even observed hunting along the reef edges using feeding patterns that scientists associate with areas rich in fish. The benefits reached beyond the water. As fishing improved, local businesses began to feel the impact. Charter captains who had once questioned the project started asking for more reef sites. Hotels welcomed more visitors during fishing season. Bait shops and local stores reported stronger sales as anglers traveled to experience the thriving reefs. A restoration project that began with discarded oyster shells had grown into an ecosystem that supported both marine life and the local economy, showing how rebuilding nature can also strengthen the communities that depend on it. The cleaning machines. A single adult oyster filters between 30 and 50 gallons of water per day. It draws water in, extracts the suspended particles, takes what it can use for food, and expels the rest. The process is continuous. The oyster does not stop filtering when the water is clean. It filters as a basic function of being alive. The reef sites at Cedar Key developed oyster populations, numbered in the hundreds of thousands. Multiplied by 30 to 50 gallons per oyster per day, the filtration capacity of a mature reef site is measured in millions of gallons of water processed daily. The water clarity around the reef sites improved measurably as the oyster populations grew. Dissolved oxygen levels rose. Nutrient concentrations, the excess nitrogen and phosphorus from agricultural runoff and development that fuel algal blooms, dropped in the water above and around the reefs. Algal blooms are one of the most damaging recurring events in Florida's coastal waters. They reduce oxygen to the point where fish die in large numbers. They produce toxins that affect marine mammals and humans. They block sunlight from reaching the seafloor, killing the seagrass beds that large portions of the coastal ecosystem depend on. The filtration capacity of a large oyster reef does not eliminate algal bloom risk from a coastal system, but it reduces the nutrient load that drives bloom events, and it does so continuously and without requiring any ongoing human intervention. The second feedback loop that developed from improved water clarity was not initially predicted. Clearer water allowed more sunlight to penetrate to the seafloor. Seagrass beds that had been lost in the areas around the reef sites, lost because declining water clarity had cut off the sunlight they needed, began to return. Returning seagrass stabilized the sediment around and between reef sites, reducing turbidity further. Clearer water allowed more sunlight through, which allowed more seagrass to grow, which further stabilized the sediment. The reef had initiated a self-reinforcing cycle of improvement that extended its beneficial effects well beyond the physical boundaries of the shell deposits themselves. The model has been adopted in Alabama, Mississippi, Louisiana, and New York, where the Billion Oyster Project has been working to restore oyster reefs in New York Harbor using a similar principle of returning shell waste to the water, rather than sending it to landfills. The concept that researchers are beginning to use to describe what all of these programs share is circular environmental design, systems that close loops between waste streams and ecosystem needs rather than treating both as separate problems requiring separate solutions. The hurricane test. In September 2017, Hurricane Irma made landfall on Florida as a Category 4 storm and tracked up the western coast of the peninsula, putting significant wave energy and storm surge into exactly the areas where the oyster reef restoration had been most active. The storm provided an unplanned and uncontrolled experiment in whether the reef structures had any protective effect on the shorelines behind them. The results were measurable and significant. Coastlines with established reef sites in front of them lost between 30 and 40%. Less sediment to erosion than comparable unprotected shorelines subject to the same storm conditions. The difference came down to what wave energy does when it encounters a rough, porous structure versus what it does when it meets an open water column above a flat bottom. A wave approaching a flat, open bottom carries its full energy to the shore without interruption. A wave approaching an oyster reef encounters the irregular, porous structure of the reef before it reaches the shore. The wave energy is partially reflected, partially absorbed by the friction of the reef surface, and partially redirected downward rather than forward. What arrives at the shoreline after passing over a reef is a diminished version of the wave that would have arrived without the reef present. The cost calculation that followed the storm was stark. The reef sites had cost approximately $5 million to establish over the program's years of operation. The damage prevented in a single storm by the shoreline protection the reefs provided was estimated at approximately $3 million. One storm had recovered 60% of the program's total cost in prevented damage, and the reefs would still be there for the next storm. Seawalls, the alternative coastal protection technology that Florida and other coastal states had traditionally relied on, cannot make this calculation. A seawall damaged by a major storm requires repair or replacement, both of which cost money and require human intervention. A reef damaged by a major storm responds differently. The disturbance of storm waves increases water circulation in the reef, brings nutrients from deeper water up through the structure, and creates conditions that stimulate larval settlement. The storm that damages a seawall prompts the reef to grow. The structures that refuse to stop, the oldest reef sites in the Cedar Key program, are now approaching 2 decades of development. What those sites look like compared to what was dropped there bears little resemblance to a pile of shells. The reef structures have roughly doubled in area from their initial footprint with no additional shell material added. The oysters that established on the original shells have died, added their shells to the reef matrix, provided new surfaces for subsequent generations, and been replaced by those generations in an ongoing cycle of growth that has extended the reef's physical boundaries in every direction. The structural complexity that has developed over 2 decades of this process was not designed. Overhangs have formed where shell clusters extended in different directions and met. Crevices and chambers of various sizes have developed throughout the structure. Microhabitats that different species require for different purposes have appeared without anyone planning them because biological systems at sufficient maturity generate complexity as a byproduct of the interactions within them. The reef is more habitat now than it was 10 years ago, and it was more habitat 10 years ago than it was in year 1. An unexpected finding that emerged from long-term monitoring at the oldest sites was the rate at which carbon was being sequestered in the reef matrix. Oyster shells are calcium carbonate. Dead shell material incorporated into the reef structure stores the carbon that was used to build it. As shells accumulate across decades, the reef becomes an increasingly significant carbon sink. The program that was designed as a fisheries habitat tool turned out to also be doing something that nobody included in the original cost-benefit analysis: removing carbon from the water column and locking it into stable mineral form that will remain sequestered as long as the reef structure persists. The biodiversity at the oldest sites is approaching levels that marine biologists compare to pristine natural reef systems that have never been commercially harvested or significantly disturbed by human activity. This is the most striking single data point in the Cedar Key story. Not that a disturbed system improved, not that some species came back, that a coastal environment that had been functionally empty returned to a condition that resembles how it existed before the combination of harvesting pressure and habitat loss had hollowed it out. The program that dropped shells into the Gulf reached its active phase and stopped. The ecosystems those shells created did not stop. 500,000 tons of restaurant waste, critics calling it dumping, fishermen expecting disaster. What grew was one of the most cost-effective coastal restoration and defense systems ever documented. $3 million in storm damage prevented, reefs doubling in size without human input, water cleaning itself, fish returning by the hundreds of thousands. Should every coastline be doing this? Subscribe so you never miss the next one.